Okay, dear friends, last time we started analyzing the CMOS inverter. Actually, this is the ideal inverter, for us, because the all the characteristics are close to the ideal inverter. I guess I draw everything at once so that the graphic is seen nicely here. So I mean, if you look at this, maybe I can draw the graphic again, and so you can maybe do this. Because this is not to the scale, so let me get this one. Okay, so if you look at the graphic again, here is the point. Maybe I should do that. Okay, so let's draw this nicely, and so that you understand the operation maybe better. 1, 2, 3, 4, 5. I don't like this. Can do this maybe better. 1, 2, 3, 4, 5. Okay, and similarly 1, 2, 3, 4, 5 volts. So this is 5 volts. This is also 5 volts. So in the transfer function, this is VTN. Okay, VTN, which is equal to 1 volt. Okay, and here, when we look at the output voltage, this is the first graphic, and up to here, transistor MN is off, and MP linear is the response. Okay, so maybe I shouldn't write this here. I'm not sure. Maybe I'll erase it again. So this is the other extreme thing. Here, this point is VDD minus VTP point. So if VTP is minus 1 volt, and this is 5 volt, then this is going to be 4 volts. Okay, so formally, but this is the case. So here, MP of MN linear is the extreme. So here, this is the line. Okay, slope of 1, and minus VTN, and this is the other line. Okay. It looks parallel. I mean, not maybe that much parallel, but looks okay. Maybe I should draw this again. That's not good. I don't like it. Let me try one more time. And that should be okay. So, here for this region, MN sat, okay, and then this region, MN linear, and then this region, MP linear for this region, MP sat, okay, and then the voltage wise, maybe we should, write the voltages here. So this is minus VTN. This one is minus VTP. And this point is VTP. So, and for the SAT region, both of them are SAT region, there's only one solution. And that one solution is going to be, if you select and do the design properly, it is going to be at 2.5 volt, and then this will be a very sharp transition. So this will be VDD divided by 2, and for which case, if this is the case where Kn is equal to Kp, or what is Kn? If you remember Kn, it is mu n times the oxide times W divided by L of N. If this one is equal to mu P times the oxide, gate capacitance per unit area, times WL divided by P. Okay, so for both transistors, this should be same. So we can cancel this and cancel this. So as long as maybe we should write it here. W L of P is equal to mu n divided by mu P times WL of N. So then the transition is going to be at VDD divided by 2. This is one case, and another case is, of course, if VTN is equal to VTP. So if both of them are satisfied, then this transition is going to be at 2.5. So this value is about, it depends on the process, but it's about 2.5. So we know that mu P is smaller than mu N. So NMOS transistor is stronger. Okay. So by doing this, so if the WL of P is equal to maybe 2.5 times W L of N, then you know, we have this symmetry generated. So let's say this one is you know, 1 micron by 1 micron. So if you make this one 2.5 micron divided by 1 micron device, then the symmetry is going to be achieved, and then the midpoint is going to be like this. So this is you know, very nice result, and the difference here, this difference is equal to this difference, and as you know, the difference is going to be equal to VTP plus VTN. So this is going to be 2 volt according to our definition. So that's going to be 2 volts, and therefore this point is going to be 1.5 volt, and this point is going to be 1.5 volt. So it will be equal to this 1.5 volt. Okay, so that's that run. So if you combine them and then, you know, complete this drawing, this will be very nice curvature like this, and then this will be very nice curvature like this. Okay, so the slope at these points are going to be 0, so very nice transition occurs here. So this will be very close to the ideal case, and the ideal case, and here the slope where it is equal to -1 can be calculated also very easily for this case. And let me draw this here. This should be somewhere around here, you know. Maybe I draw this wrong. It should be somewhere around here. So maybe I can, oops. I want to only erase this one. Ah, both of them are gone. So I'm trying to do this, you know, perfectly. Okay. Oh, not so good, but it's okay, you know. You know, from here, we know that this point is 2.5. 2.5. Okay. So this is the midpoint. So this point is V input low, and the value of V input low is equal to 1 plus 2.5 divided by 2, because that's everything is symmetric. So it's going to be 1.75 volts. And similarly, if you look at the other point, it's going to be here. Right, this is going to be the point. So this is going to be the slope. Slope is equal to this one is going to be input high, and V input high point. Maybe I draw it wrong here. V input high is going to be equal to 2.5 plus 4 volts divided by 2. which is going to be what? 3.75. 3.25. 25 volt. So probably my drawing is not, very correct. So that's going to be the input high point or voltage. So if I want to make this thing perfect, maybe I should, oops, too much is gone. So I shouldn't do that, okay. But as you see here, when things are very symmetric, it will be easier to draw this and then obtain input high, input low. Everything is very symmetric here, and the transfer function looks like similar to. What is similar to? Voltage transfer characteristic VTC is very close to the ideal inverter. Okay, because if you remember the ideal inverter, this was the ideal inverter, right? This is VDD, and this was VDD divided by 2. So this was the response. So here our response is very close to this, but maybe here you have this and here we have this. Okay, so this is CMOS. This one is ideal. So that maybe this is now showing the CMOS properly, and this, I guess I'm using the slides a little bit different than what is meant to be. So the symmetric VTC is obtained this way. So input high, input low definitions are already, I've done it here. So maybe I should, I did it already, input low and input high, yeah, in this graph. So I can skip some of the slides here. So I want to show one more thing to you, but I'm not sure how to show that. Maybe I'll draw it here again. If I select the devices not to be symmetric. So if this one is 1 micron by 1 micron, let's say this one is 1 micron by 1 micron. What will happen to the, to the circuit? So let's select this one as 1 volt, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So this thing, let's draw this. And this one is going to be -1. This one is going to be -1. So this is -1 volt and then -1 volt. And what was this one? This was minus VTN. This one was minus VTP. So, you know, this will be same, the slope. And maybe I should do it like this. Okay. So now, let's draw this again. Maybe this is 5 volts, 4 volts, 3 volts, 2 volts, 1 volt. And this is 1, 2, 3, 4, 5 volts. If the, you know, here, Kn is not equal to Kp, okay? And let's say minimum size transistors are selected. Okay, and then minimum size, L minimum is equal to 1 micron, W minimum is equal to 1 micron. Okay, so in the design, if you do that, what will happen? So the transition, I mean, no matter what WR ratios are, this will be valid. And then this will be valid. Okay. So if you select that midpoint or transition point, we in where both transistors are SAT, SAT voltage. For this case, if you calculate this, it happens to be, I mean, if you do this calculation, I gave you the equation. What was the equation? I guess I wrote it down somewhere around here. Yeah, here is the equation. VDD minus VDD minus VTP, absolute value of VTP, plus VTN times plus VTN times square root of Kn divided by Kp divided by 1 plus square root of Kn divided by Kp. So if you select this to be 2.5, this is supposed to be 2.5, and then this one is 1 volt, this one is 1 volt, and then this one is like that. So this will be about 2.16 or 16, yeah, volt or so. I mean, you can do this calculation yourself. Probably it's going to be 2.16. Okay, so it's not going to be that bad. I mean, so if you look at this, this will be here. So the transition is going to be happening again at one point, and then you just need to combine this here. We need to combine this here. Okay. So this is the point, 2.16 volt. So again, it works like a nice inverter. Okay. So no matter what you do and select, Okay, W L of N and W L of P, you know, it's independent of W of N of L and then values. This structure will result as a, nice inverter. Operating as an inverter. So it is independent of WR ratios of the transistor. Of the WL ratios of the transistors. Okay. So this is called, therefore, ratioless design. Okay. So in any case, no matter what it is, V output high is going to be VDD, and V output low is going to be 0 volt. Okay. Very nice feature. Okay. Okay. So this is why today in industry, more than, I guess, 90%, 95%, everybody goes for CMOS. So the definitions, we can skip the definitions, but I guess we will be coming to CMOS inverters, CMOS cross-section, power consumption issues. Yeah, later on it's going to be seen. So that's it. So if, you know, this response can be either here or here or here or here, you know, depending on different WLs. WL ratios. Okay, but you know, there's going to be a sharp transition, and then this will be always the case, you know, no matter what it is. This is going to be the case, and this will be VTN. It's going to be VTP. VDD minus VTP. That's the voltage. Okay, so CMOS is very nice. Okay, so even for minimum size transistors, this will work. So input high, input low definitions we have already done. So this will be the slope. This is going to be the slope. This is going to be V input low, V input high. If it is symmetric, then it's very easy to calculate V output high, VDD. And let me just fill this quickly. V output low, 0 volt. And those are the definitions. So we can find the transfer function using the load line analysis, but the load line analysis is a little bit complicated, because for each value of Vn, gate to source voltage for this one, and this one will be different. Drain to source. When we source the gate of P, this is the gate to source of N. So it will be changing. I guess this is the reason that I'm going to, skip this load line approach, but basically, we will be having lines here. So these are going to be for PMOS. This is going to be drain to source of N, which will be equal to I source to drain of P. And this will be N, which will be equal to VDD minus V source to drain of P. So for each value of Vn, we will be using this one. For example, for this value of Vn, we will be using this value for corresponding this. So this one is, let's say, the gate to source of N is equal to 0 volt. Here is V source to gate of P is equal to, VDD minus Vin. So therefore, this is going to be 5 volts. So 5 volt graph will be used corresponding to this one. So the solution is going to be 5 volt. And that's what it is for if input is equal to 0 volts. Right? Input is 0, output is going to be 5 volts. So graphical analysis can be used, but we have to, again, select different colors. Let's say for this one, which is Vin is equal to 2 volts. This one is going to be the corresponding 3 volt thing. Input is equal to 2, so this will be we source the gate of P is equal to 3 volts should be used. Okay, so therefore the corresponding solution point is going to be this point. Okay, so this is how it goes, and can be calculated. And then you will be noticing that at 2.5 volts, both of them are going to be in saturation. So there's going to be a line like this, maybe somewhere around here, 2.5 volts, 2.5 volts gate voltage. Both of them are going to be in saturation for about 2 volts. So that's what corresponds to this line. Okay, so this one is going to be VTN plus VTP line. So I guess this explains the graphical operation, graphical drawing of the device. So if you look at the cross-sectional view, how to implement these devices, this is it. We have this NMOS here, and this one is PMOS device. And in order to connect circuit-wise, what we do is, now this is circuit connection. We connect the bulk to here, and then we connect gates of both transistors and apply here Vin. And then drains are connected, and this is going to be corresponding to Vout. And this one is connected to VDD. Okay, circuit-wise. And why do we need this N plus? So that we can have an ohmic contact for the metal. So that's why we use N plus in here, because this is N well light the dope. So therefore we need N plus to get a good contact to that node. And then similarly, this is we talked about this in BJTs, right? So this is the device. So maybe draw this here. So the bulk is connected here. This bulk is connected here. And that's the device. This is V out. And this is V in. So we use some other models for the transistors. We don't really need to. This is what VLSI designers prefer for this device, VDD, and then ground here. Okay, so no need to show the arrow. This is drain and source. This one is drain and source. This is gate and gate. So this is how we prefer, because we consider this as a switch device. Yeah. Okay. And the idea is to make a switch here, as simple as this. So we have a switch to the inputs. Depending on the input, V out is either connected to VDD or connected to ground. Okay, so this is how we represent the transistor. I mean, I know that you learned a lot of things in the past. I hope we are recording. And that's the eventually what it comes to. It's reduced to this. So another nice thing is the power consumption. So power consumption is when static, maybe static power consumption is power consumption when output is low plus power consumption when output is high divided by 2. And when output is low is the case where Vin is equal to what? VDD, right? If this is VDD, then MP is off. So I, source to drain of P is 0. So therefore, this is going to be, VDD times I, output low, IDD, times IDD, output low, which is going to be 0. Okay, divided by 2 plus VDD, IDD when output is high, divided by 2. So both of them are going to be 0. So PD static is going to be equal to 0. What? Okay. Great. Okay. So this is another very important advantage of this device. So, however, if we think that, you know, this is going to be a load capacitance is here. So, if Vin is switching between high and low at a frequency of F, then each time, you know, the capacitor will be charged. Maybe I'm going to say that this is charged. While this is being charged, there's going to be a voltage here. We source drain of P, okay, voltage, and then times I source the drain of P, current, while charging. And then, you know, that's going to be creating a power dissipation. And while discharging, let's say this is discharging, the other cycle. So then there's going to be V source or drain to source of N times I drain to source of N. You know, therefore, there's going to be power dissipation on MP and MN. Okay, so there is a power dissipation on MP and MN while charging and discharging CL. Okay, this power dissipation you can calculate this actually, and maybe I'll you know, I'll send you this, but so we call it, this power dissipation is called as dynamic power dissipation. So P dynamic is going to be equal to frequency of switching times CL times VDD divided by R square. So this one is what we will be still dissipating power. So static power dissipation is 0, but this one is going to be now the dominant factor here. So this is also valid for the TTL circuits or some BJT based devices, but we typically ignored this one because the static power dissipation was dominant at that time. But here static power dissipation is you know, 0, so you know, we need to look at this, and especially if you use a you know, microprocessor where there are, let's say, you know, 100 million gates, and then each of them are switching at a frequency of 1 gigahertz, and this is very high, 1 gigahertz, and then all the capacitances that needs to be charged and discharged, you know, is going to be significant. So, but you know, people, you know, when you use 5 volts, this becomes, you know, 25 you know, volt square. So therefore people started to drop this voltage to you know, this value. The effect of supply voltage is coming like square effect. Therefore, this is like, what is being done. And then later on, people drop that to maybe, 2.5 volt, 1.8 volts, maybe, lower 1 volt or so. The whole thing idea is to, decrease that value. So a significant advantage is obtained here by supply changing the supply voltage. So just before, going to this fan out ideas, one other thing is maybe important to mention here. This, we said that this is ratioless. Okay, so this is ratioless. And for which value, no matter what the WR ratio, this will work. Another important thing here is that maybe we should just point out, okay, it is supply voltage, VDD, also does not change this fact. I mean, as long as VDD is larger than, as long as VDD is larger than VTP plus VTN. So let's say for 3 volts, this will also work properly. So for, devices here, let's say, if supply voltage is dropped to 303.3 volt, this will work. But maybe at 1.8 volt, threshold voltages should be selected, VTN and VTP should be small, for proper operation. Okay, so let's give a break here and then look at the timing analysis of these devices. Or what shall we do? Give a break and continue, or continue a little bit and then stop early? Let me stop here today.
Today, like all? All class?
Yeah, today. This is now after the exam. So is it okay? I mean, I can continue if you want. I can cover a few other subjects, but let's stop it today. Okay.
Okay hocam.
3 saatimizi tamamladık.
Hocam dersi bitireceksek ben bir şey sorabilir miyim? Sesim